Wait, so are you listening on 161 something, or is that right? Or like what?
I just had it on the FM at 91.
Okay, so I think KCSM also transmits on 161.
Really?
It's the channel that that they send for the AM stations. So it's between the stations. They'll have these direct high quality FM, well, low quality FM, but good SNR that they will transmit then from the main radio station into the repeaters that do AM, like the retransmit on AM.
Interesting.
Yeah, so what people sometimes do and used to do is that you know what the channel is, and then you just sit really close to that station, and then you do, like, you key with your radio, and then you get transmitted on KCSM. Because you're always going to be stronger. What the hell? What's going on with these students? Look at that. Maybe I'm going to do a pop quiz. That's going to, like, if you do well, it's going to clobber your midterm. All right, I don't care. I'm excited. Welcome, EE123, lecture 31. Woo! I think I'm going to stop I'm going to stop this recording thing for the next from the next class. So we've got a bunch of invited speakers coming up. And this should be amazing, but I'm not going to record them. Like, you have to be in class if you want to be able to hear them. On Friday, what I'm going to do is I'm going to talk about a project that came out of this class. It's a fun story. I'll tell you about it next time. But it's about detecting cells in microfluidic channels. And how would that even relate to this class? It's an interesting story. Faculty for mechanical engineering was interested in a DSP student that would go and do some analysis on some of the data, and she wanted to present in class, and she presented, and I was like, oh my God, this is so cool. And so we started working together. As it turns out, it's really relevant to whatever whatever is going on, from filtering, match filtering, detection, and also even successive interference cancellation with sparse signals and things like that. So it's all related. I'm going to talk about this on Friday. Monday, we have Laura Waller talking about computational imaging. Next Friday, the Friday after that, we have Balint Sieber. He's the guy from the video from Edis Research. He's a SDR evangelist. Well, he used to be his job. Now he's involved in security. It's related to wireless security company where he looks at, what happens when stuff is emitted to the air and people can pick it up. What can you do about this? How can you hack a system, but also how can you protect the system from being hacked? Because everything leaks, right? I showed you this example where the bus, on your computer, actually emits radio, and you can use that to either transmit information or maybe even figure out what's going on there, okay, or what command's being issued just by listening with a radio. Okay, so we got a nice bunch of speakers coming up here. Okay, so there are just a little bit about the project. Everyone needs to meet with me. I told you, but there was so many still open spots on my schedule. But now I'm getting these emails like, "Well, your schedule is full." Yes, it is full now because today's the last day. I'll try to make more spots today, and I'll post them for those who have not met with me. But I think most you, right? You. I'll add more. The reason is I want to meet with you. Okay? I want to talk to you. I want to know what you want, and I also want to give you some tips so that you're well prepared to get a good project. Okay? And of course, you're more than welcome to meet with John and Frank. I think actually talking to them is probably more useful than talking to me, but I also need some attention. Okay, so there were no shows. So today everybody has to meet with me, and I'll post them more. Yesterday I recorded. There was a really nice ISS pass, and I posted it. And this is the picture I recorded. Unfortunately, I missed half of it, just because I was holding the antenna, and then I pulled out the USB audio. And then Audacity didn't work, and I had to restart, and then by that time, half an image passed by. But look at the quality; it's pretty good. So the signal-to-noise ratio is really, really nice for this pass. And you posted, right? You posted one on Piazza. So what did you use? What antenna? But it's still a what kind of antenna? A whip antenna, still with a whip. So even with a whip antenna, I was able to pick up. It was a really nice pass, at 80-something degrees. And today there's one at 79 degrees at 3 p.m. So come to the Hearst Mining. We'll give it a shot. Campus with noise going around. I never know if you're gonna pick something. I'm hopeful. So bring your radios. You might actually be able to pick up even with a rubber ducky, maybe. But I'll bring a few antennas, so you'll see a demo of picking up signals from the ISS. There's a special event. I think the Russians are transmitting 12 images. They cycle them. It's a 3-minute protocol. It's called PD180, and that's also slightly of a problem because it takes 3 minutes, and the whole pass is about 10, or less than 10. So, and then they have 3 minutes in between. So there's no much chances of maybe missing half a picture. Yesterday was so close. This is how it sounds like. Oh. That was a pretty decent recording, I think, that came out. Okay, any questions before we move on? Yeah.
So it's assessing it's fully invertible,
Which one?
What the object is that you're measuring, you'll be able to reconstruct it.
That's a good question. Well, okay, so if it's continuous, it is invertible. That's right. If it's continuous time, continuous space, continuous radon transform, it is fully invertible. But before we move on to this, yeah.
Oh, you have a question about this?
No, before this, before we move on to this. Any questions about anything else? Okay, today I'm going to talk also about Lab 6 if we have time at the end. Lab 5B. We changed numbers. But, if we have time. Okay, yes. So it is invertible if it's the continuous, but it's not necessarily invertible if it's not.
So this radon transform, we just do this rotating this kind of like line. Aren't these double sample, like lots of extra samples at the origin?
So we're talking about here's continuous.
Well, when we sample,
Right.
we have lots of like kind of lines that rotate, but at this origin point we count that extra times. That
Yeah, right. There's a density there.
Right.
There's over-density, and hence you have to compensate maybe for that density. That's where the Jacobian comes in. That's why we need to do this pre-filtering, or the row filter that we talked about last time, because of this compensation for the density. In fact, you have way more measurements in effect when in the discrete, basically the measurement goes up linearly, right, as you go up. And that's why you need to compensate with this row filter, part of it. But if you think from the continuous point of view, right, if you think about this, like there's just more density concentrated in the polar coordinate, right? And then if you move to Cartesian coordinate, then you have to compensate for that density, and that's where the Jacobian shows up. Okay, when you switch to these coordinates. Basically, every r where you are in the radial, right, as you move to the center, it increases the density, and hence the Jacobian has to weight that down by that exact same amount. Which is interesting, though, because when you get to 0, then rho equals 0. So where's that sample? Right? Like what happened to DC? Goes away. Well, at DC, if you think about it, then it's really like almost an impulse. So in the limit, they actually compensate. So in the continuous time, at DC, it becomes impulsive because you have infinite density at that particular point. And so multiplying by 0, right, compensate for it. So it's if you have to think in the limit. Okay, what happened in the DC? Okay, right, because the density goes, increases, and then this decreases. The weighting has to decrease in the same amount, but then the value has to be 0, and that could be a problem when we do discrete. Okay, because discrete that limit doesn't happen. Okay, so we'll get to that. Okay, so just going back, yep. This one? So this is rho. So P of rho and theta, right? So rho is where you are on that axis, and theta is, it's a 1D Fourier transform. Okay. So you over rho, right? Over rho. Yeah. It's a 1D Fourier transform over rho. That's right. That's a good point. Yeah. Right, and theta would be just the parameterization, like which angle you're doing. Thanks. Okay, so the projection slice theorem tells you that we covered last time, and we proved it. Tells you the following: if you have a 2D object, you make a projection, basically line integrals, through the object at a particular angle. Then you get the projection. The 1D Fourier transform of that projection is the same as evaluating the 2D Fourier transform along a line. What an awesome theorem. Beautiful. Okay. The beautiful thing about it is because now we can understand that if we rotate, we get another measurement in the 2D Fourier transform. And in effect, we can cover the entire 2D Fourier transform by making these projections. So that's the information that we're getting. We know now what type of information we're getting. And then we proved it last time. So then we try to say, okay, how do we then go about and reconstruct it? Okay. Where is that information? How does that relate to each other? We went through and we did first a partly discrete reconstruction in which we have continuous theta and discrete rho. If we have continuous theta and discrete rho, we have projections that are evaluated now discretely. We then compute the DTFT, and now we have a continuous 1D DTFT. And we put that on the 2D DTFT of that object. And in that case, we've got, again, a continuous space, okay, of the 2D discrete Fourier transform. Okay, so we can cover that for all possible thetas and all possible, basically, so theta and rho. And now we said, okay, let's try to figure out how do we compute the inverse 2D DTFT of that function, right? We have a 2D Fourier transform. We want to compute its inverse. If we compute the inverse of a regular 2D DTFT, it's just a double integral from minus 0.5 to 0.5. And again, I'm using the notations of k, which goes from minus 0.5 to 0.5, as opposed to omega, which goes from minus pi to pi. The nice thing about this, I don't have to divide here by 1 over 2 pi, so it's symmetric. But it's exactly the same thing, because 2 pi times k is really omega. Okay? So 2 pi times k is omega. So same thing. So I do the double integral, and I will get the result. But now I don't have f of kx and ky. I need to change coordinates. Right? I have it in f of rho and theta. I don't have it in kx, ky. And so what I do then is when I change coordinates, if I want to integrate over rho and theta, then I need to add this Jacobian, which is what we call the rho filter, this weighting in the frequency domain that compensates for that change of variable. Because in rho and theta now, the domain has different density, in effect. Okay? So when we go to polar coordinates. So it's more dense when we're getting to the origin, and then it's less dense when we go up. And so this is equivalent to that. That's exactly the same integral. So if I have my data here, all I need to do is multiply by rho, and then compute this integral, and I would get my result. So this is a reconstruction. Right? That's a reconstruction. This is done. If I have my DTFT on a polar coordinate, all I need to do is compute this integral. So this is my data, my DTFT in polar coordinates, multiply by rho, compute this integral, and then I've got myself an image. That's all I need to do. Okay? So it's invertible. So we must multiply by this rho filter. Okay, so now I want to go and talk about what happens when we have discrete angles too. Okay, so this is the more practical situation. So now let's assume that we have discrete angles, theta sub m. So now I have indices, right? M indicates what angle I'm going to be. So for a particular m, I'm going to have a particular theta. Okay, so that's my discretization here. And then I've got n, which is really where I am in the radius. But it's all now indices. Okay, so m is discrete, n is discrete. Okay, so now I make this projection. I've got measurements, p of theta sub m as a function of n. I compute the DFT now. And in this case, I'm computing the centered DFT. Okay, so it's slightly different. Okay, it's the centered DFT. So where k, I guess L equals 0 is in the middle. Okay, that's the DC. So it's not the usual thing where L equals 0 is at the that side. Okay, so centered DFT. And so I have this now discrete signal, which I'm going to map into the DTFT domain. So these are really samples of the DTFT of that object, right? The sampled object. And then when I make more projections, I will have this data along these projections. Okay? So how do we do the reconstruction? What I'm going to do now is I'm going to replace all the integrals with sums, okay? Like we did for the DTFT, where we integrate over the space. Now I'm going to replace all those integrals with sums for both radius and angle. Okay, so instead of integrals over radius and over radial frequency and then angle coordinates of frequencies, I'm going to now replace those with sums. And what I'm going to do is I'm going to define this thing, and bear with me here, okay? So this is kind of a long expression, but it's really exactly the same as before. So just pay attention, okay? FL comma theta m. What is that? That's really samples of the DTFT. Okay? Samples of the DTFT in the of the DTFT of our object. Okay. What is this here? This is really the discretization over the thetas, the right thetas, and the right. So where I am in the angle and where I am in the radius. Okay. And I'm going to make, of course, n samples, right? So I need to divide by n, okay? Because I have only n samples. So this L over n is really rho. Okay, L is the index, where I am, in the radius, divided by n will give me rho. So the total number of samples that I have. Okay? So that gives me rho. And that goes from minus half to half. Okay? That goes from minus half to half. I have sine of theta sub m. Again, this is the discrete version. And then I'm going to sum over L, and I'm going to so in this case, I'm just going to define what's called a back projection. And the back projection, pay attention, doesn't sum over thetas. It only sums over the L's, just over the radius. Okay? So I'm just summing over the radius, and I'm applying this weighting in the frequency domain, which in the time domain, or the signal domain, not the time domain, but in the space domain, correspond to some convolution, right, filtering, right, or a circular convolution in this case. Does this make sense? So weighting in the frequency domain correspond to a circular convolution in the space domain, but here I'm only going to sum over the radius. I'm not going to sum over the angles. So what is this really? This is an image. It's a 2D signal because it's still a function of nx and ny. It's also parametrized by theta sub m. So it's going to be different. This is a set of signals, a set of 2D signals, which I'm going to call back projection. Okay, or in this case, actually, a filter back projection. And if I take all these set of signals and then I sum over them, that basically means I'm going to sum over thetas. Right? If I sum over all of these that are parametrized by theta m, if I sum over all these theta m's, then I will get myself the reconstruction. But I want to define this first, because this is a very interesting operation, this back projection. So this is the filter back projection. This part over here, if I sum over the m's, then I would get basically the sum over of the thetas, which will give me my signal. Okay, I was repeating it many, many times, so it sinks in. Yes?
One of these C thetas corresponds to one of the lines.
Yes. So every theta sub m corresponds to one of the lines in the frequency domain. That's right.
Then that's that rho factor when m is going to be equal to 0.
Yeah.
We'll never be sampling the DTFT at the origin. Right?
Yes, you don't.
So we never know. We don't care what it is.
You'll see what's going to happen. We're gonna correct for that. Yeah.
The lines never overlap. Isn't the only point that's to make the DC term the same? Because
Which one?
since the the lines only ever change angle. They never. There's no point where they would ever overlap, right? And since it's DC, except at DC, but since it's always zero there, is the sum even necessary?
This sum?
Yeah, because it feels like.
Well, wait. This is just the result, basically, for a particular theta. So if you have just one line, and then you just compute this operation, this sum, over the radius, but now you still parameterize by theta. So you've got really m signals here. Yeah.
Yeah, but if you change the angle.
Well, wait, let's second.
Overlap,
Right.
right?
Wait a second. I could have added another sum over here, and then it would give me the image. Right? But I'm not. I'm just parameterized by theta. Basically, I'm taking one line, and I'm doing an operation, which I call back projection, which gives me an image that is parameterized by theta. I'm going to show you what it is right now. I'm just going to show you. So if you want to avoid actually going through the center, then I could have shifted this by half. Okay? If I shifted that by half, then I don't have that problem. Okay? And that's often actually how it's done. Yep. You could do it on a continuous case, yes. But I want to compute that on a computer. Right? Okay. So here's what it is. Here's an example. Let's say I have this object here. If I make projections, the projection from this direction looks like that. The projections in this direction looks like that. The projection in this direction looks like that. Right? Because that's the shadow. And the projection in this direction looks like that. Okay. So now I'm going to define the operation of this back projection. Okay, what does that even mean? So here's basically the back projection operates on the result of a projection. And then I'm going to sum the result of these filtered back projections together to get an image. This is what I'm doing. Okay. All right. So for theta equals 0, the projection is really the sum of FL0, L over N, the sum of that. That gives me a projection. Okay. This is a projection. I'm sorry about that. Again, this is the back projection. Okay, back projection. How do I compute this? What it actually is? Okay. So I have my projection. How do I compute this? Okay, how this is computed? This is the DTFT, right? Evaluation of the DTFT. Now I have my projection. I want to do that. How do I do it? What I do is I take my projection, I compute an FFT. Now I get FL and 0. Okay, this is FL and 0. That's F and L0. Now I multiply by L over N. This is the row filter. This is how it looks like. If I want to compute the back projection, or the filter back projection, the way it's equivalent to is taking the IFFT of that, which gives me this value, it's a one-dimensional signal, and then go and smear it through the entire two-dimensional space. Just like take it and then smear it. Why? Because it doesn't have any other value for x. I mean, for y. It's all the same for all y's. Right? This is a function c of nx and ny, but when I do this filter back projection at theta equals 0, there is no really y participating here. Right? So it's the same at all y's. So I did this operation, I get this filter back projection. I get this filtered projection, and then I back project it by taking it and smearing it, replicating for all y. Okay. I can do that also for all other angles. So this is C0, theta sub m equals 0. Right? I can do that also for another projection. For example, for c over pi over 2. So theta sub something, sub m not equal 0, that corresponds to pi over 2 angle. If I do that, I take this projection, I compute the FFT, I multiply by this rho filter, okay, in the frequency domain, take the IFFT, get this result, and then smear it. And what is my image? The image will be the sum of all these filter back projections, right? So here are how it looks. This is my object. This is filter back projection for theta equals 0. This one, if I add it, this is the filter back projection for theta equal 90 degrees. Okay? So, and then I'm going to add another one. That's from an angle. And then I'm going to add another one. Right? And so now, here's all of them. Summed together as I rotate. Now, on the right, that's the filtered back projection, the one that I use the rho for. On the left, I didn't apply this rho filter. So I didn't compensate for this weighting. And if I don't compensate, I get this blurring, really. Because I have more density in the low frequencies, right? So they're emphasized. And so it's really not, this is actually the result. Okay, so if you don't do the filtering, multiplying by the rho filter, then you get this. If you just do back projection. If you do the filter back projection, then you get this. Okay? You want to see it again? It's beautiful, huh? I know. It's gorgeous. As I add more filter back projection to each other, then you see now the object is being built. Right? And you can see kind of what the effect would be if I don't have all the angles. Right, if I only have partial angles, yeah.
I'd like to say that was so awesome. It sent shivers down my spine.
Right? No, you want to do it again?
No.
So this is the beauty of tomography, right? And it's so simple. You take the projection, you convolve with a rho filter in the signal domain, or you do that in the frequency domain by multiplying by a rho filter. And of course, you can think of, well, maybe I don't want to emphasize the high frequencies. Maybe I want to do a rho and then tapers off, right? So it could be, people come up with all sorts of ideas like that. And then you compute this back projection and add all of these together. And this is one of the most common ways of implementing a reconstruction of the radon transform in discrete, not time, but in discrete measurements. Discretely. There's other ways that you can do this. For example, I can perform an interpolation of the non-uniform Fourier transform onto a Cartesian grid and then perform an IFFT. So I can do some other sorts of solutions, and there's many type of algorithms that people came up with in order to do these type of reconstructions. You can also solve it as an inverse problem by applying a forward Fourier transform, or a forward back projection, inverse back projection, and it will automatically correct for this rho filter. And so there's many, many type of approaches. Okay, but this is the most common way that this is being done, and it's awesome. So now the question arises, right? Like somebody asked me before, is it invertible? Who asked me? Is this invertible? Is this invertible? The question is how many projections, and what is the sampling that I need to do along the along the projection, in order to be able to reconstruct an object. Right? You can ask that, how many projections? Obviously, I'm going to show it again. This is not enough. 3 projections are not enough. That's what I can get, right? Out of 3 projections, 4 projections, not enough. And then here, if I only have part, then I really don't have all that information. And there's actually a lot of application where people are trying to, they have a situation where they have a limited angle. when they want to image something. So they could rotate only a few degrees. So limited angle tomography. And so there's inherent ambiguity there in the reconstruction. You can still do something, but it's never going to be the best. Or maybe it's going to depend on the object too. So how many projections? Any idea? How many projections? It could be right. It could be right, but it depends, right? It depends on what? On my image. But what part of my image? What part of the object that it depends on? Its size. Absolutely. Depends on the size. And so if you think about this, again, we're sampling where? In what domain? Like each projection really gives you measurement in what domain? Through the Fourier slice theorem. In what domain? In the frequency, right? Each projection gives me a line in the frequency domain, right? So you can think of it as sampling in the frequency domain. And what is sampling in the frequency domain? Who cares if it's frequency domain or space domain? Like they're all interchangeable, right? So if you think about this, if this, for example, was the spectrum and this was the image, I would have had to have a certain rate that I would need to sample such that I don't have aliasing of the frequencies. Now the case is that this is the image and this is a spectrum, and I effectively make measurements here. So I need to have a certain rate such that I don't have aliasing. Now, what's a bandwidth in one dimension? Well, what's the opposite? Like, what's the alternative of a bandwidth in one domain? How you represent that in the image domain? What does it mean bandwidth in the other? The size, right? Size of the spectrum is the same as the size of the image. Right? If I have a larger size, then my frequency domain is going to oscillate faster. Okay? If I have larger bandwidth, my time domain is going to oscillate faster. Okay? So that's interchangeable. And so in that case, the spacing between the projections at the highest frequency that you want to resolve needs to be proportional to 1 over the field of view, which really is kind of like the bandwidth. And also the spacing along should also be 1 over the field of view, but those are usually not as limiting as this. Right? Because that's defined by your detector density, and this one is defined by how many projections you're going to be making as you rotate the object or you rotate the gantry. So if you do that, this is actually the result. So here's what happens. So for this object, 256 projections actually are within the Nyquist rate. This is like the equivalent Nyquist rate. If you do 128 projections, something starts happening. By the way, do you see this Gibbs ringing? You know why it's coming from? Well, I'm going to effectively filter, right? Like there is a limit to how much sampling I have of the projection, right? I cannot sample it at infinite resolution, right? So I'm going to effectively have a finite resolution when I go to discrete time, right? So effectively, I'm kind of low passing the projection before I compute the DFT. And that could be an analog or can be just aliasing that could happen there too. But that's the effect. Okay, so you get Gibbs ringing because you have finite resolution, right? So now you cannot have impulses. You can have only kind of sinks. Yeah. The next one? Yeah.
When you say projection, you're talking about how many lines we sampled,
Yeah. How many how many angles?
Does this matter at all? How much sampling you do along the line?
Yes, absolutely. So first of all, if you sample too sparsely, then you can get folding too. Right?
Is there an interplay between the two? Like, can you make one larger, one smaller, or one smaller, one larger?
Usually the dominant issue is really not the sampling density here, but really the sampling density between. This is defined by your array, like how fine your array is, and this is how much you rotate.
But can you compensate one for the other? Saying like, I have limited angles, but I have really good precision on my arrays. Nope.
Well, if you think about it, like you really need to have some certain spacing between your samples. Right? So the answer is no. But the effect of not having that will be different.
So when we're looking at the back one, the spacing between the samples wanting to be inversely proportional to the field of view, wouldn't the sample the farthest away be the one from there to the one to the left on the one below on the left, so something closer to the origin?
So if you think about this, that could be actually sampled faster than Nyquist.
I mean,
Right? This would be the further away, right? And that, so what happens is actually that sometimes in the low frequencies you're actually sampled at Nyquist quite often. But it's the high frequencies you need to care about.
yeah, I mean,
So I'm not sure of the question.
so if we're checking the distance, like in that domain between the two on the farthest,
Yep.
that will be. Do we only want to compare, like, say, the fifth sample of this angle to the fifth sample of this angle? Because the fifth sample of this angle will be farther away from like the first sample
Yeah.
of this one.
So we want this one to be about 1 over field of view from this one. This sample from this sample.
Okay.
The furthest away. And if you don't, that means that the high frequencies are going to alias. And so you get this result, where you start getting high-frequency aliasing or streaking artifacts. Because you're violating. I reduce the number of projections. Now I violate the Nyquist criteria. I violate it only for the high frequencies, not for the low frequencies. And so I got this kind of streaking artifacts. Like they're not actually so bad. As I go to 64 projections, so now I'm well below Nyquist, I'm getting more streaking artifacts, and more and more and more, because now more and more frequencies are going to be aliasing. But if you notice, the aliasing is not coherent. It's not like I would have undersampled uniformly in the, like if I had a Cartesian grid, if I would have sampled uniformly, then I would get completely different aliasing. I would get wrapping of the signal on top of each other. Here, the result of not meeting the Nyquist criteria is that I have this incoherent aliasing. And if you remember when we talked about compressed sensing and sparsity, I mean, I can kind of see the image through it, and my aliasing kind of looks like noise. And one of the first applications people have applied those ideas of compressive sampling is to this type of application. Because you can, by exploiting sparsity of this object, can actually recover it from fewer projections. Even though you didn't collect all the necessary data, but because the sampling is, in this particular case, gives you this low side lobes of interference. If you know that the object is sparse, for example, this object is piecewise constant, you can actually recover it. You can recover it even from 16 projections in this case. Yeah.
That's only because this object itself is sparse.
It's sparse, right. And if it wasn't, then that's not the case. Yeah. So again, we're kind of start closing the loop in some way. If you think of what is the sampling, what's the density, what will be the effect then in 2 dimensions, right? You can create this natural non-uniform sampling that happens from physics, the fact that you're making projections, natural non-uniform sampling of the frequency domain that maybe allow you to still use ideas like sparsity in order to recover better images. All right. So then the question. So this is really not the geometry though that is acquired on modern CT systems. Modern CT systems use this fan beam type of a architecture where you have an array of detectors along kind of a radius. Like a circle. And then you have one source. And the one source basically shoots X-ray through the object and is detected by these. And so you get more measurements at the same time, right? Like you don't need to align an array of, or you don't have to do it one at a time. Or to collimate. Often what used to be done is that you had to put a collimator to make sure that you only get a projection from a particular angle and not from other angles. Okay, so that reduces signal to noise and so on and so forth. Now this is how it's done. And so you've got a single source, many detectors, and the question is, how do you reconstruct? The way it works is that this rotates around the object, and then you get the data. And the question is, okay, how do I reconstruct? This is not a projection, right? The data I'm getting now is not a projection, really. A projection needs to be flat, right? So what do you do? Oh, nice. Yeah, that's a great. So it's called rebinning. So basically what you do is you say, okay, when I have this projection, if I have this angle for cone beam CT, then this measurement here, it's like having this line integral at this particular point for this particular projection. And it's the same as, the one from here. Right? So now I have, kind of two of them. Okay? All right. So then if I have a different angle in my cone beam CT, that will correspond to a different line in a different angle. And all you need to do is just sort them. And once you sort them, and if you made 180 degrees minus the fan beam angle, then you got yourself your Nyquist of having all possible angles that you need from all angles. Right? So it's 180 minus the fan beam. So you really don't even have to do a full circle in order to do. Yeah.
So CT scanners, though, they don't do less than a circle, but they just keep going.
As it going like this, then the patient's like shoved in. So you actually get what's done. It's called a spiral CT. So, in fact, it's even more complicated. And so there's some approximation often that they do if you want to do a direct reconstruction, because you really never have a full projection. Right. So it's not discretely moving. It's like actually the patient lies on the table and it's so fast that they have to first accelerate. So they accelerate the table. Patient moves in as this thing is rotating, and then it has to slow down, and the patient's kind of like almost, it's like, it's really fast. And they also have up to 256 slices. So in fact, there's 256 slices that rotate of arrays of detectors that you could do. Now, the more slices you have, there's other issues that I haven't talked about, and that's if you want to take a medical imaging class. When you shine X from here, there could be a result where this is scattered and that creates photons that are detected by this. And so the scattering kind of adds like a noise interference. And so that could be a problem when you have all these arrays of detectors. That increases the scattering. Okay, so that's something that they have to deal with. Yeah.
So, obviously, in the medical devices, you can reconstruct the image by getting many slices
Yep.
for the full 3D object. But does the theory still hold if you wanted to put an object inside a spherical cage and then have the camera rotate in rho and phi as well as theta to generate the 3D image as well?
Of the inside?
No, just to generate the 3D object. So here you're taking, it's in just theta is which you're rotating in, and you're moving in a linear fashion to generate the slices. But could you have a camera that could go in both the rho and the phi direction?
Yeah, but that's stitching, right? Yeah. Pretty much. This is just an interpolation. You can actually measure that, and like, yeah, you can take even 1 pixel, right, from each place and kind of scan it from all direction. So you could do that, but you need to know the distance, right? So there's algorithms how to do that, but it doesn't give you the insight. In fact, if you have light that you shine on an object and then measure its shadow, you could reconstruct using tomography the convex hull of that object. Okay, but it has to be the convex hull. You can't really reconstruct what's inside. And if it's a non-convex object, then you can't really. There's some ambiguity there. Okay? Doing tomography with optics is very difficult because optics also have like through objects that are transparent. There's also phase aberration, so there's diffraction that happens, and it's not just attenuation. But X-ray, there's very little diffraction that happens with X-ray, and that's why we can do this type of tomography, when you can think of line integrals as opposed to like waves that are propagating. There's also electron beam tomography. There's also other type of tomography. Even people are trying to do ultrasound tomography, which is very, very difficult. Yep.
How can it survive take pictures from 180 degrees if you never get a look at the other side of the object?
What do you mean?
So there's always going to be like this dark side of the thing that you never.
Where?
Like if you only move it for 180 degrees.
Yeah.
Yeah,
you can. It doesn't matter if you look from this side or from this side, right? They're equivalent. That's equivalent. Right? It's the same line integral. There's no directionality. Right? For the shadow, it's just a line integral. Line integral I can reverse.
So then was it the same? When we had an array, could we only take it for 180?
What do you mean?
So when you had that animation, right?
Yep.
Picture wasn't.
Yeah, 180 degree would be fine. I did 360, but yeah, you don't need to. You just need 180. Yep.
We should be like kind of restricting ourselves in the sense that we're only doing straight lines. And I know you can do like a line integral where you're not a straight line. So are there ever any circumstances when some sort of variation in the projections like theory would apply and we wouldn't have straight lines in our object?
Right, but you need to know what those lines are.
Yeah.
Otherwise, it's a severely underdetermined problem. So yeah, you could have basically any. I mean, the question really is, if you discretize the problem, is that matrix invertible? Right? You can write that as a matrix vector operation, right, of line integral. Just make different sums, right, of my object. So it's basically matrix multiplications. Here in this case, positive numbers. In MRI, it's actually not necessarily even positive numbers. You can actually have negative, even complex numbers in your matrix. Right? In ultrasound tomography, they have that kind of a problem where sound waves go in one direction, but they can actually turn and change. And they also change velocity. So the density of the integral changes as they move through the volume. And this is like seriously a hard problem. Still, people can make some assumptions and solve some of that issues, but it's a huge problem if you don't know what the matrix is. If you know, then that's fine. For example, if somebody put a mirror here or some lens, X-ray lens, right? If you know what it is and what's properties, then you could solve it. But otherwise, it's very difficult. Yeah, what happens actually if you have a metal bar here, for example, you have an implant that X-ray don't go through, then what you get is an artifact because you actually don't have a measurement of what's inside. And it also obscures whatever is after that. And so you get some inconsistency in the data, and you get some artifact. These are called beam hardening. That's the language that people use. It's pretty awesome, right? All right, so I didn't have a chance to talk about Lab 6, which is fine. I'm going to talk about it on Friday then. Lab 6 is going to be posted tomorrow. So not Lab 6, Lab 5 Part B. It's all about digital communication. And what you'll do there is, in that part, basically you're going to take a sequence of bits, you're going to modulate them using audio frequency shift keying, and then you're going to write a demodulator that will demodulate them back into bits. with also the ability to synchronize when those bits occur. Because if you have somebody that's transmitting, like, you don't know where it starts. So we're going to add that part of synchronization, which is not part of the class, but I think it's important to know, kind of like some tricks of the trade. Okay? So this is that part. The next part after that is going to use a transport layer. So you take this physical layer that you created in part 2, and then you add, you put it in a packet structure. And in that packet structure, you are able to do some routing, error detection, and now be able to implement what's called the APRS protocol, part of the AX25 protocol, which will allow you to communicate with other stations that people put up, in Berkeley and other places. Be able to then send packets that contain information, to send yourself a text message, to report your position, to send an email, or to text message between each other.